professor at the Universidade Federal Fluminense in Niterói, and I'm a co-chair together with Wickerson Andrade of SAST here in CBSoft. We hope you enjoyed SAST and all the CBSoft events so far. We had excellent presentations. For the session closing session, we have a great invited speaker, Dr. Baishakhi. She'll be talking to us about systematic software testing for deep learning applications. It is a really amazing topic, and I think Baishakhi is one of the best names to talk about the intersection between software testing and AI. She is assistant professor in the Department of Computer Science in Columbia University in New York, and has been working in the intersection of software engineering and machine learning. Professor Baishakhi has received many Best Papers awards, and her research has also been widely covered in the trade media. She is a recipient of the NSF Career Awards, VMware Early Career Faculty Awards, and IBM Faculty Awards. Thank you very much, Baishakhi, for being here with us, and you can start when you want.
Thank you, Vania, for the nice introduction. And hello, everyone. I don't want to introduce myself again. I am Baishakhi, and today I am going to talk about systematic software testing for deep learning applications. So, deep learnings, in particular, deep neural networks are increasingly used in safety critical systems in today's software ecosystem. For example, we all heard about the autonomous cars. Then they are also used in malware detection, medical diagnosis, aircraft collision avoidance systems. So these systems are safety critical, right? They cannot tolerate like simple errors. And if the underlying DNNs that are in this system, embedded in these systems, make mistakes, then the effect can be even fatal. So with this kind of application, it becomes increasingly important to test thoroughly how good the machine learning model is that is embedded in these systems. So saying that, it is not only for these mission critical systems, DNN is becoming so pervasive, they are almost becoming like a new paradigm of software. So you can think about deep neural network as like software 2.0, as said by Andrea Karpathy. Probably some of you have heard about him. He's a director of AI at Tesla. So as we are seeing these new type of software, we will also see the new type of bugs, and let's call it by Andrea Karpathy. Probably some of you have, and let's call it bugs 2.0. And these bugs can be very serious. Probably, again, you have heard about some of the errors that especially autonomous vehicles are facing. So for example, in 2018, I guess, Tesla was driving, a driver was driving a Tesla in autopilot mode, and it was driving in a very bright condition, and there was a white truck in front of the car. So the car could not distinguish between the truck and the white sky, bright whitish sky background, and basically collided into the car. So, and then it was fatal. Unfortunately, the car driver died. Another accidents happened where Uber was driving in autopilot mode, and suddenly it was very dark in Arizona, and uh, bicyclist came. He was crossing the road, and then the Uber bumped into her. So these are some of the very real life sad accidents that happened when a car was driving in a autopilot mode. And there are several other examples. I just picked two of them to give you a sense that how fatal it can be. So seeing that, hopefully you are now convinced that DNN-based these autopilot cars are not robust against these realistic corner cases. So, this is a very extreme scenario where you have a like very bright sky and a white car, a white truck is um, driving in front of it. So this kind of like corner cases, you need to test your car, and it is very difficult to write test cases. And we will define, we will describe what test cases mean for testing machine learning models. But coming up with this particular test case is very difficult, because there can be millions of such corner cases. So the question becomes, with this, like how we can systematically test this DNN robustness for such realistic corner cases, right? And so let's step back and think about what is robustness. In traditional software engineering, we talk about robustness all the time. So I just took this definition of robustness from Wikipedia, and let's review it. A robustness is the ability of a computer system to cope with errors during execution and cope with erroneous output. So most of us probably know and familiar and work with this definition of robustness. But what does robustness mean when we talk about machine learning model? Well, there is no established definition yet, because one of the reason it is difficult to exactly apply this robustness definition to machine learning based systems, because machine learning based systems are probabilistic systems. So by design, they will incur some error, right? So we have to, while defining robustness, we have to incorporate that characteristics of machine learning systems. And with that, in the literature, I think this is kind of a working definition. And I am sure that will evolve as we do more research in this domain. But again, as of now, we can think about, for machine learning algorithms to be considered robust, either the performance is stable after adding some noise to the data, or the error with real data should be consistent with the training time error. So what does that mean? The first point says that if I train my machine learning model with some data, with slight variation of those data, the machine learning model should still behave similarly, right? And we will come to that point later. And then there is another point that say, if I train a model with some data, and then obviously that model will have some error by definition, but when you are applying that model in real life scenario, the error rate should not be way beyond the training time error rate. So hopefully the point I am trying to make, when we are defining robustness, we have to incorporate this probabilistic nature of the system in mind. So this kind of robustness is little bit different from the um, standard accuracy measurement in the system. And the reason is, the standard accuracy measures happen when, so you have a basically data, you divide the data in training set and testing set, and the testing sets and training sets come from the same distribution, and you train the model on your training set and test on the testing set. But for robustness are measured, or I mean using real data, so that may not be exactly similar to your test data set. Saying that, obviously it will not be completely drastically different. So for example, if I have a image classifier, and I trained it to distinguish animals, I cannot probably use it to identify cars, right? So that would be unfair. But what the expectation here is, if you are training the machine learning model to identify or distinguish between dog versus cat, but then with slight variations of dog versus cat, in real world, it should be, successfully identify that. And so that is the real data. And then there is a generated variance. So if we even change a little bit, say environment, or maybe rotate, or do some little bit changes in the image, your model will still be behaving properly. And these are the two kind of um, requirement based on which we will build all the robustness model that we will discuss today. So let's see what kind of generated variance I mean. Uh, and say we can generate variance simply by adding noise. These are typically called adversarial example. And I am sure, most of you have probably heard about it. So this is a classic example. You have a pandas picture, and you add some adversarial noise, and then you ask the machine learning model, give this noise added picture to the machine learning model, and now the machine learning model is classifying it as given. So this is a typical adversarial example where you and this typically uses to attack the model. There are also, you can imagine, generated variance with natural variance. So for example, you have a road condition, your car is going along the way where the arrow indicates. And now you say increase the contrast, and you can imagine you are using a better camera, right? Or to increase the contrast. So this is a completely natural variant without any active attacker. And in such case, we will see that the car with a car, is going to a very different direction. It is basically going off-road. So the model is making mistake. And this is an example of like generated variance with natural transformations or natural condition, you can say. And finally, there are also other kind of generated variants that are studied in the literature, where you have a picture, and now you added some irrelevant objects on that top of the picture. Say, for example, here you have a stop sign, and imagine you added some stickers of bottles or something else on the stop sign, right? So a human will still find this picture as stop sign. However, to a car model, to a car model which will make decisions seeing this stop sign may make like unwanted decision. So these are some of the variants or the noise, basically variants you can imagine that are type of variants that is studied in the literature to test robustness of a machine learning model. And in some of our work, we tried to see the properties of these variants, like what is happening, why the machine learning models are failing when uh, we are giving these variants. So I just wanted to show you a couple of examples, like how brittle these models are. Hopefully some of these properties can illustrate that. So in this figure, we took around 1,000 images from the same class. It is a deer class. And then we added noise within, adversarial noise. So in the left-hand side figure, this is an unmodified model we tested. And the original deer class was represented by this gray region. And now with adversarial image, these different colors indicate different other classes, like say automobile, airplane, etc., etc. And as you can see that with adversarial noise, the deer classes are classified to all sort of different classes, like bird, cat, horse. So it's like all over the places. And that is quite bad, right? We don't expect that. And so from left to right, we have different models that are more robust. So these models are trained with with the objective of adversarial robustness. And you can see, at a very high level, hopefully you can see that now the adversarial, there are more deer classes, because these pink dots are adversarial deers, and they are more closer to the original deer classes. The more sophisticated the robust models are, they are more, basically it is becoming harder to distinguish between the adversarial deers versus the the original deers, and which will be our intention. As you can see, the right hand side figure which we proposed in our paper, where all these these different separations are all together, so it will be very difficult to distinguish between natural deer and adversarial deer, because they are like very close to each other. So with that, here is another example. If you, taking a close look, what is going on. And here, say we have some truck pictures. Each green dot represents a truck picture in the representation space. And then all the birds are represented in blue dots. And the red dots are basically adversarial images of the bird, which are misclassified as truck. So again, from left to right, the model's robustness is increasing. And as you can see, the least robust model, which is A, all the adversarial birds are completely into the wrong class. And as it is going to the right, they are pushing more towards their right class, and which is basically what we want to do. So basically here, at least for image classification kind of model, it is all about, our classification is mostly about finding the boundary between the classes, right? And here the robust models are trying to increase the boundary and put the adversarial images to their right class by pulling them towards the right class. So that is the kind of visual representation I wanted to present, just to uh, give you like what is going on. And also there is another thing, interesting thing, I would like to mention, that even within same class, the robustness can differ. So in this picture, the top picture, we took a bird and rotated it in different degrees. So say for example, with 0 degree rotation, that means the original bird, it is classified as bird. But when we make 6 degree rotation, it is classified as airplane. Then with 24 degree rotation, it is classified as cat. With -9 degree rotation, it is classified as dog. So you can see this image is completely brittle, right? Like with slightest variation of the rotation, it is classified as very different kind of image. However, we took another picture from the bird class, and then that class went through similar kind of rotation, but in all the rotation it was still classified as bird. So this is also another property where the robustness property is more like local. Each image can show different properties, though though two different images can have very different robustness properties, though they are in the same class. So with this, today I would mainly focus on robustness under natural variants. So basically, what does that mean? That these kind of variations can naturally appear all the time without any active adversary, and testing a model with such natural variants is very important, because they can happen in real world all the time, and these data are mostly unseen. So with this, I would like to talk about two kind of natural variants. One is the one I just discussed so far, that robust with a model should be robust with natural variants like under rotation, increasing contrast, etc. And we will also talk about some the model's robustness with unseen real world data. So let me start with the robust model robustness with natural variants. And here we will talk about the robustness with respect to testing self-driving car. But I think the message should be applicable to any systems that are using machine learning models, at least in vision domain. So as we all know, the autonomous cars are becoming more popular day by day. Most of the companies, major car companies, are investing the possibilities of self-driving car. I think a car with some autonomies are already on the road, um, like semi-automatic kind of car, and there is a prediction that by 2035 there will be almost 26% of the cars have some kind of autonomy. So it is very, very important to test these cars, right? However, these cars in real life have already driven millions of miles in autonomous mode, and 20 United States passed legislation to enable autonomous driving. Um, and let's see what is there inside the car. And this is a typical autonomous car I am talking about. So in general, inside the car there is a machine learning model where the model takes input from different sensors, like camera, lidar, infrared sensors, etc. And the output of the model is the decision that car make. So it can be steering angle, like how much your angle will be changed. It can be applying brake. It can be accelerator, etc. And inside this model there are neurons, and just to give you a context, each neuron takes some inputs, and then they have some weights there in this along the edges. Then we compute the sum of these weights and inputs, and it goes through an activation function, and then each neuron gives some output. So this is a very, 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 very basic background of how each neuron work and how overall the neural network works. So in this work, we only focused on camera input, which takes images from the camera and outputs the steering angle. So for example, your camera is taking this picture, and after going through the neural network, the output will be like go straight. The arrow, red arrow indicates here that you have to basically drive straight. And this is in general how the car works. I mean, the model in the car works. You have a car where you implement this model, and you drive the car in a training environment, or you can also use some simulator to train the model with different scenarios and in which direction the car should move. And then you embed this trained model in your car chip, and then the car started diving. You gather other image or scenario, driving scenario. You again then retrain the model and so on. So this is usually going on in this active learning setting, where as you accumulate more data, you retrain the model accordingly. So however, testing this kind of system is little bit different than the way we are testing traditional software. So for example, here are again some of the reason why it is different, but again the list is not comprehend. I mean the there are many other reasons. So first reason is that DNN logic is not encoded with control flow. And if you think about traditional code coverage based testing, then they are essentially dependent on the branch coverage and control flow, right? So that's why it cannot be directly applicable. Similarly, DNN models are highly nonlinear. The activation function that I introduced, it's a nonlinear function. So traditional symbolic analysis kind of technique again will not be directly applicable. So we have to think about how to build new technique or new metric to compute, to test a deep neural network model. And here is a technique that was proposed by Pai et al., which is based on neuron coverage. And the basic idea is that, as I said, for every neuron, it takes some inputs, and then each inputs are associated with a corresponding weight. The neuron itself take those inputs and weights, and then with their activation function compute a output. So what we did is, I mean, what they did, not we, I mean, Pai et al. Did is they computed a threshold, and if your output is beyond some threshold, they annotated that neuron as activated, or if the output of that neuron is less than that threshold, they said that they thought that the neuron is not activated. So based on this definition, the neuron coverage is computed. So basically, total number of activated neurons over total number of neurons. So here is an example. Say I have, in this network, I have total 7 neurons, and 4 of them are activated. Then I can say that my neuron coverage is 57%. And how do I decide that the 4 of them are activated? Say my activation threshold is 0.75, and with the computation, like 3, with the input and weight combination that I just talked about, if the output is here 1, so that is obviously more than our activation threshold, so we say the neuron is activated. So and this was proposed by them. We took that measure, and we tried to test, I mean, check that whether neuron coverage can be a useful measure to test a DNA-driven self-driving car. So to do that, we basically took these 3 models, Chauffeur, Rambo, and Epoch, and they are implemented with CNNs and then LSTMs with like, they are pretty big standard model, and these models were one of the top models in Udacity self-driving car challenge, which is very popular self-driving car challenge. So the first research question was, do different input-output pairs result in different neuron coverage? And here the idea we wanted to say, we check that if we have one image, I mean, one image with some driving angle, it is produced. So whether these different kind of combinations are activating different neurons, because if all these input output pairs are somewhat activating similar neurons, then the neuron coverage metric will not, we cannot use it to test self-driving car. And we did that. So how, whether these different neuron coverage and the input output diversity are correlated, and as you can see from the result that yes, they are strongly correlated, so which is great. Then we can basically use this to test our underlying models. And next we try to synthesize different realistic scenario by maximizing this neuron coverage. So the idea is very simple. You take a image, then you say, for example, increase its brightness, and then check, pass it through the neuron and monitor its neuron coverage. If the coverage increases, then that's great. You take that image for further mutation. And if it does not increase the coverage, you basically discard it. So I think in search based software engineering, we use similar techniques many times for traditional software. So basically we implemented a very similar technique of search-based software engineering, software testing for the self-driving car. And here we use 9 realistic image transformations such as rotation, blur, rain, fog, etc. So to give, I mean, to basically generate more and more diverse images. And here the search technique we use is basically greedy search between the transformation to find synthetic images. And our fitness function is to increase the edge coverage. And the next we check whether these different transformations, whether they are covering different neurons. And as you can see from this picture, basically what we did, we compute, say we took all the, for one image we took all the rotated version and then check how much different neurons are activated with as compared to the original image, and we compute that based on the Jaccard distance. And as you can see, with significant higher Jaccard distance, that basically with different transformations different neurons are activating. So with that, with this notion, we basically generated many natural variations of the original image. And then that's great, but then how do we test it, right? I mean, that's what we wanted to do. So our goal that check the output with metamorphic relation. And so basically what the intuition behind is that with increased brightness, output of the DNN will not differ much from its input image, right? So they will be somewhat similar. For example, you can see this, say you trained your car in the left hand side image, and say you are driving in a sunny day, so things are a bit brighter, but you should still follow the similar driving angle. So, but saying that, it is not so simple for self-driving car, right? So when I say similar angle, it's not exactly same. It requires a range. So some notion of statistics, like from this, I mean, say previously if my driving angle was 20-degree, now my driving angle can be 20 plus minus some error. So with that notion, we define a statistical metamorphic relation to ensure that. And let me explain what that is. So this is a classic regression plot, if you are familiar with that. So here, say I have 3 points. The original or expected ground truth output is theta1, theta2, and theta3. And my model is predicting P1, P2, P3. So my mean square error will be given by this formula, where basically we are computing difference, that how far my prediction is off from my ground truth data. So based on this MSE, we define a MSE transformation where we are computing how far the transformed images predictions are with respect to the ground truth. And then the metamorphic relation for testing self-driving car that we defined is that these this distance between theta and the transformed images prediction should be within some error bar of the original MSE. That means basically you are tolerating overall similar error that your original model is predicting. And lambda is a parameter. If you want to tolerate more error, you can do that. It is your choice, right? So with this metamorphic relation, our bug condition becomes that if the distance between the ground truth and the transformed images prediction is greater than this lambda times original MSE, then it is a bug. However, there is another problem. Say if you increase your transformation so much, say for example you rotated with absurd some degree like 50-degree, then obviously your car will, I mean that's not realistic, right? So your car will fail. And um, so those violations will be clearly false positive, and we don't want to report that. So for that we created another filtration condition where we will only choose those parameters, that means only choose those transformations parameters whose overall MSE is within certain error bars of within certain error bars of the original MSE. So basically overall with that transformation the car is still behaving correctly, and now for particular image we can check whether that is a buggy transformation or not, or not buggy transformation. So basically with that transformation whether the model is producing a bug producing transformation. So here is an example. On the left hand side we have this original image and the arrow shows where the car is going, and now we added rain, and as you can see with the arrow the car is going completely on another road, and it will basically collide with the car that is coming from the opposite side, and hence we can produce a crash. So there are many more such synthetic images. If you are interested, you can see in this website. And here is a small video I would like to play. So your car is going, and then fog happens, it is crashing, and again it is crashing and colliding with the car. So basically here you can see without fog the car was doing fine, and then as the fog comes it started bumping. So here is some evaluation with I mean we, as you can see, we can find like many erroneous cases for this self-driving car. And while we check, the false positive rates are rather low. For example, with fog, we can found more than 4,000 errors and so on. I don't want to just uh, iterate the number, but overall the thing is that the takeaway point is that um, we can successfully find many errors in these cars models. So the next question is that obviously what we will do with these images, right? Fine, we now know the car models are brittle, they are not robust. Just to check as a proof of concept, we retrain those models with those buggy pictures. And what we found is basically that when we retrain it, the retraining is pulling down the MSE, which is mean square error. So basically, the synthesized image are making these models more robust. So with that, we basically have seen that deep test can systematically test the DNNs, and we found thousands of erroneous behaviors in these top models, and also retraining can help these models to make more robust. So with that, I slightly want to show you a completely different kind of error that can happen in a machine learning model, and this is for this unseen real world data. So as um, you know, the DNA, the image class, not self, I mean, this is not again a self-driving car, but these are very simple, say, image classification application where we are talking about. So this was a famous error that happened where the Google photo application were tagging some of the uh, like black colored people as gorillas, and there was a huge uproar. Of course that should happen, and we definitely, I mean, you should not have this kind of classification, right? And then there were again another news, some funny application where the Google photo confuses a skier with a mountain and basically says that this is a mountain. So these are very confused. Your model becomes very confused. Also, these models suffer from bias errors. That means when a woman is cooking, the model is correctly classifying that human being as woman, while when a man is cooking, the model is incorrectly classifying that human being as woman. And I mean, again, this is, I mean, we probably all know these models suffer from such bias problems. So in this work, we were testing an image classifier for such confusion and bias errors. And the classic scenario of testing is that, say, a developer wants to check for confusion and bias errors before deploying a model in the real world, that whether your model suffers from this kind of, I mean, scenarios which will, I mean, which will be very harmful to your reputation, right? So setting is that you have a trained model and you have a bunch of real world unseen data, and you want to see how your model is behaving. So we tested it in two scenarios. One is single level and one is multi-level. The single level is, say, in these examples, you are only identifying whether it has, say, cloud or it has sun, etc. And in multi-level, one image can have both sun and cloud, and you are expected to identify both and saying that, okay, this image is tagged with cloud and sun or all three. So it is multi-level, right? So again, here is some example of single level confusion. Say you have a DNA which tends to predict class X with class Y, and you can see a real example taken from ImageNet where a cello is classified as violin. And for multi-level, if you have an image with class X, our DNA tends to falsely classify Y, a class Y, where Y is not there in the image at all. So for example, in this image, there is no mouse, but the DNA is saying there is a keyboard and mouse. So here is our formal definition of confusion error. So basically, what is given a class Y, what is the probability of mispredicting it to class X and vice versa? And basically, we take a mean of it. And if your confusion error is beyond the confusion threshold, which we define the confusion threshold, then we say that we have an erroneous condition. So for bias errors, we have a notion of third object. So for example, look at the right hand side figure. Whenever a woman is in outdoor, it is I mean, the she is most likely classified as men, and we found it in many real scenarios. So here we have this third condition, that if outdoor is present, then women can be classified as men, and this is like a bias error we define. Similarly, languor is more likely to classify to Macau than screwdriver. So here there is a notion of like two classes are biased as with respect to another class. So again, as I said, this is a kind of triplet notion of confusion where we have three class X, Y, and Z, and we are computing what is the confusion errors, the difference between confusion errors between these two classes. And once we have this confusion disparity score, then we can compute the average of all the confusion disparity. And again, if your disparity is beyond certain threshold, we can say that these three classes are suffering from bias. So, okay, that's great theoretically, but how do you define those confusion and bias errors? So, if you have noticed, there is a concept, I mean, this is a notion of distance between two classes. So if I have a class X and if I have class Y, in some representation space, in some form of representation, if these two classes are very close, then they are prone to be confused, right? Because neural network cannot identify them. So basically this distance between two representation of classes are inversely proportional to the error. And similarly for bias error, there is this notion of another class Z, and the thing is that Z is here closer to X but far apart from Y. That means Z is biased towards X, but I mean, with respect to Y. And so this is basically, I mean, you can see in the representation space, what does it mean? These two errors, like how these two errors look like. So now, I mean, look at this function F. Here the function F means it's some form of representation. It can be the raw image, that can be a representation, the vector of raw image. It can be some embedding, like final layer embedding, or it can be something else. So basically the question is that how do we get the representation of the function F? And in this we use again the neuron activation, but think about it. Here we are talking about class level property, like say this car, like woman is, I mean, the model is biased for man with respect to woman. So we are no longer considering a single image, but the properties are class level properties. So we need a representation in neural coverage, even in neural, I mean, in all this representation space, we need a class level representation. So that's what we did here. Here we proposed a probabilistic neuron activation per class. So basically what each PJI means that for each neuron J, what is the probability that it gets activated by an input of class I, and then we define this metric. And then if two classes in this probabilistic space are very close, then they will be suffering from confusion error and bias error and so on. So again, we tested this scheme with many multi-level state-of-the-art models, multi-level, single level with many classes. And there are two baseline where we randomly picked some class pairs as for inspection, and then we also have a baseline which was this paper was FSC paper, where I mean they used it for debugging purpose, but somewhere we basically choose a representation space which is taken from the final layer of the neuron. So with this, we are running out of time, but I just wanted to emphasize that basically our model is performing a little bit better than these baseline. Actually, I mean, 72% than baseline. With mode, it is around 30% better. So overall, the results look promising. So for both confusion error and bias errors, and then I mean if you are interested, please check our paper. So overall, here I wanted to introduce two type of very different errors that I mean the confusion and bias that often DNNs face, and we talked about some testing tool that are like that you can use to find those kind of errors. So with this, I think there is a long way for the software engineering and machine learning techniques that should go. Software engineering, especially I work in this testing area, and you know that we have to offer a lot to make these models more robust. Saying that, there are many domains where the machine learnings are used, and these domains have different properties. So we have to uh, look at these domains, look at their properties, and then basically formulate the testing scenario accordingly. And this is a wide opportunity of research, even if you are thinking about these different domains. So few, again, not exhaustive, of course. Right now what we are seeing is just tip of the iceberg, but as we move forward, interesting questions come, that how do we test and debug machine learning systems. There are very few works on debugging, and with that, different domain, more complex applications, the way how you are presenting your test metric, etc. Also, you should think about once these models will become mature, how to maintain these machine learning systems, like how can we modularize, how we can leverage existing test cases. What do you mean by adding new features in this setting, and so on. So with that, I think thanks for listening, and I am ready to take any question.
Thank you, Baishakhi, for your nice talk today. So we can start now the questions. Anyone who wants to make a question can put it on the chat, or write on the chat, or also turn on the voice and video and ask. If you have problems with asking in English, you can also write in Portuguese and I'll try to translate. So Valdivino has one question.
Yes. Congratulations for your talk and for your work. Very nice. My question is related to the thresholds. I think that in both studies, you have some thresholds.
Right.
Do you automatically choose the values of these thresholds, or it is done manually?
That's a very good question. Actually, I created a backup slides for that. That was the immediate backup slides. So for the, I think you will get the idea. So what we did here in the second part of the talk, there is this standard deviation of of the confusions. If you think about confusion, like, you know, in general, what are the confusion values look like, the distribution of confusion values, and the threshold we choose, which is basically one standard deviation from the mean values. So the errors will be beyond one standard deviation. So most of them will not be classified as errors.
Okay. Okay,
And
thank
then,
you.
yeah.
Patricia Machado also has a question.
Hi, many thanks for the excellent talk. I just wonder if the challenge of testing is related to the size of the network somehow, or the kind of learning model that you use. Do you have any insights regarding this? I mean, does the size and the kind of model pose additional challenge or not?
Sure, of course. So I mean, the size and complexity of the network definitely poses more challenges. I mean, saying that, you know, it is not clear yet where you will actually test. I mean, so a lot of testing technique usually form this representation that I talked about, this final layer. So if you are only looking at the final layer, then probably the size of the network will not matter that much, right? So it depends on how you are formulating your testing, or at which point you are probing. I mean, there are also some work in other community where they say that up to certain initial layers, most of the learning happens, and after that, I mean, those layers are not super important. The outer layers. So what I am saying is that it kind of depends what you want to test and how you are formulating your testing metric.
Okay, thank you.
We have another question here in the chat.
Yeah.
I don't know if Jose Cesar wants to take, or can I read? Jose Cesar. Okay, so I think I will read. Thinking about the currency, urgency on explainable AI, interpretability, fairness, and other related terms, how do you see that current machine learning testing approaches can contribute to explaining automatic machine learning decisions to end users to support personal data protections regulations such as GDPR?
I see. Yes. So that's a very good question. I mean, so I think I don't know what exactly you are meaning that. So basically, are you kind of talking about like whether you can think about like data leakage, privacy challenges, things like that? So I mean, if you are in, I mean, that's a good, there is no work I know of, at least from software engineering side, that we are looking at those yet, but those are very relevant. I mean, again, they are probably not directly related. Well, I mean, they are kind of different kind of testing, right? Where, say, for example, in traditional software, we talk about security or data leakage property testing, which will be that kind of testing in machine learning, where we can see what kind of leakage we can find from those from probing the network. So yes, I mean, eventually they will all be very relevant, and they will, I mean, different kind of testing notions will form, right? Like today I only talk about robustness testing, and then I in my research group, we are mostly focusing on that, but definitely this data leakage kind of, or privacy kind of testing will also become very important.
I have one question. So I think that when you, in traditional software testing, when we see the coverage of white box criteria, we can imagine, you can wonder what kind of input we can use to test the code. But I imagine that when you are testing machine learning, a deep learning application, I don't think this is possible, like to figuring out what kind of input we can think about to activate or to cover that neuron. Is it possible? I don't know.
So this, Vanya, I mean, I think this is again related to the, I mean, explainability of AI, right? Since we do not know, I mean, what the machine is learning, I mean, these kind of question, like where what you are asking basically, what do this metric mean? We don't know, right? This is just some metric which is showing interesting correlation, and that's all we know so far.
So that's why we needed to work on with the corner cases and try to figure out the most the corner cases do you want. And probably that's the problem that you told me, that it's just we just need to, all the domains have different different complexity, different challenges, and we need to
Absolutely. Or even like, even if I cover say 100% neuron coverage, I mean, which is kind of true for code also. Even if you reach 100% code coverage, that does not mean your software is free from error, right? These are just some metric that increase your confidence. That's it.
Okay. So in this way, we cannot guarantee that we have robustness in our model, in our deep learning application. It's possible. Yeah. Okay. So no. Okay. Another question is like, for a research that it is used to work with traditional software testing that wants to start to working with now testing of machine learning application, what is the way that this research should follow, in your opinion?
Can you read it again? I mean, sorry, I could not follow.
For a researcher who is used to work with traditional software testing applications, but now he's wanted to start to working with try to in the testing of machine learning applications. In your opinion, what's the path, the way that this researcher needed to follow?
Oh, I see. Okay, that's So, first of all, I should say most of the machine learning models that I have seen is very brittle. So finding bug is not a big deal there. I mean, yeah, you can basically find bugs in this model all the time. I think somehow abstracting away the behavior of this machine learning model and then identify like either a common class of bugs that your testing techniques can find, or basically come up with a metric, I mean good metric that can kind of push the bar. I think those will be more those will be interesting direction.
Okay. I think that's I know that's just Esteban here.
I can see a question.
Esteban, do you want to talk? Okay, so I think I read it. Unlike traditional software in which the bugs are usually related to code written by the developer, it seems to me that in AI applications, the bugs are normally associated with problems in the process of training the models. I would like to know your thoughts about it. I believe that perhaps we as a tester should pay more attention to the data that is used to train the models.
Right, so that is a very good question. Yes, the way I see it, that the machine learning models, like there are three sources of bugs. One is in the data, one is in the model, like say I choose a bad model architecture, right? Or I choose I did not train the model enough. Those things can happen. And then another very interesting is that this intersection between model and the data, like, because we have seen, one image, say one data point, which is buggy in one model may not be buggy in another model, right? So that means there is an intersection region, where different model is treating that image differently. I think while reasoning about bug, we have to, basically think about these three things, like the model, data, and the interaction.
Okay. So, any more questions? Valdivino wants to talk.
About the last definition of bug in the context of machine learning, don't you think that, I understand that you talked, it's very interesting, but don't you think that eventually you have a really bug in the code when implementing a model? For instance, it is not worth it to try to find bugs in the traditional way that software testing community does. I mean, there is a wrong, incorrect instruction in the code. There is a bug that, as you know, don't you think that it's not also worth it to pay attention for this kind of issue?
So you are saying that,
because for instance, one causes the model. Eventually, you have an idea of a machine learning or deep learning application, but eventually you incorrectly implemented it in code. This is the traditional definition of bug that you usually use in the software testing community. Okay, so that's the point. And if we look at as what we can call our scientific computation, we have lots of kinds of these mistakes. For instance, round error, floats error is something like this that may impact in the computation. So don't you think that in addition to the kind of bugs that relate to the data, also to the model, the implementation of the code is not relevant to take in account in an ML application?
So yes. So implementation of again, it should be taken into account, because there are again there is a paper again. People started showing that, say, if you are using different libraries, the different bugs are coming. One of the main reason is that floating point errors, accumulation of floating point errors. So definitely that is important, absolutely. But the so I think the implementation error is somewhat will in the long run will impact less, because they are very kind of small code, right? Like if you just initialize a model and then the model will learn by itself, right? So it's a very small code where you are basically defining the architecture. It's not like imperative programming where you are step by step deciding the logic.
So, in your opinion, they are not as relevant as the problem the training set or something like this can impact more in the applications.
Yes, so what I think, the implementation, like say library errors, it will have a huge impact because any model that is using it will be impacted, right? Okay. However, like this the traditional bugs, like developers are making logical mistake, that impact might not be that big.
Okay, thank you very much again.
Yeah. Thank you. Thanks. That was a very interesting question.
Renato also wrote a question in the chat. Renato, do you want to talk? Okay, so great talk. While testing the models, your experiments were made in partnership with the data scientists who made the models. Besides knowing what to test, when in the process of creating the model, should the data scientists introduce tests in the model in modeling per se, as in a test-driven development way, afterwards in a quality assurance fashion, or both?
Okay, so so far for this kind of work, I collaborated with vision researcher, but not like data scientists who work in industry. And so based on vision, I mean, my collaborators are mostly from academic setting. So saying that, I think those people are mostly concerned about like traditional accuracy testing, where they're testing this in distribution data and then how to push that with different scenario, of course, but they were not too focused on the robustness testing angle, where like with different, or they are not also trained to think about the corner case, because their point was, if my model works in my testing scenario, that's good enough. I mean, that's kind of the most of the mainstream people are working, and then they are proposing more sophisticated model to push the standard accuracy high with they may be, introducing more sophisticated data set, they are solving these annotation problem, etc. I think while we are looking, as opposed to those of my collaborators or mainstream vision researchers, we are looking at these corner case behaviors, or focusing on some particular bugs, how we can find them, how we can fix them, and things like that. So I think that is your first question. Second question, afterwards, in a quality assurance fashion or both, so it depends. So I have a student who works in Google, and he said, I mean, if nothing works, they just throw away the whole data set and then they start again in their particular project. I'm not saying the whole Google does that. In their particular project for mobile testing, they do something like that. So, the problem is that I think the whole machine learning testing is not not so mainstream yet. It will be, I'm sure it will be mainstream, and they will do this kind of quality assurance testing eventually. I don't think most of the teams are doing this testing so rigorously, except probably the self-driving car people, because their safety is very serious issues.
Okay, he puts another compliment here, if possible. Do you believe your analysis would be easier if the data collection was made thinking about creating test set that would exercise the corner case?
I don't think so, at least for general purpose vision, even if we are considering only vision, because think about, I mean, these real life scenarios are basically everything, right? That is going around us. So no matter how much you pay attention, there will be infinite corner cases. So definitely with more such robustness, knowledge will in data collection is great, but still I think we should do more, as much as possible, rigorous like testing, because no matter how much, I mean, even in traditional software, right, which goes through so much testing, in very security critical software, we are still seeing bugs. And here, I mean, we are basically, at least the expectation is, you will learn from all possible real world scenario, which is, with the current technology, it's like, I think it is almost impossible with the current technology, current knowledge. And we are basically trying to augment that.
Okay, so any other more questions here? So I'd like to thank you, Baishakhi, again for your nice presentation, nice talk.
Thank you.
We have a channel on Discord, and if the participants want to have more questions, you can put the questions there. Or also, I guess you can send the email for Baishakhi. Thank you again for the presentation. It's a pity that you are not here to meet you again in person in Natal. Anyway, just to finish the session, I want to say that the SAST Awards is going to happen on the closing session of CBSoft on Friday, and we have a award for the best paper, and see you all of you there. I don't know if the CBSoft organizers want to say something before finishing. Okay, so thank you again. Thank you all for the participants, and I hope you enjoy the other CBSoft events that is going to happen this week.